Hello, I'm M. Freeman. I've been doing data science since the mid 90s. That's a decade before the term got coined, and that's actually the point of this channel. Our field has had a lot of different names over the years: data science, data mining, machine learning. But as the names change, the principles for doing it, they don't change. Today, I want to talk about data science as a design field. Data science is usually thought of as an extension of software development, but it actually has a whole lot in common with designing. Now, my guide to design thinking is the book by Nigel Cross, Design Thinking. What he does in this book is talk to designers, go through design projects in a lot of different fields, and then extract principles of how to do it and how designers actually work. I want to go through four of those principles today and show how they relate to data science. The first one, and this is a really big one, the spec is the start of a conversation. When a designer, it's called a brief in their world, gets a spec, it's the start of a conversation to how to get to something better than the client actually thought of. Now, often a designer will actually do two different solutions, one of which is exactly what the client asked for to get paid. And then a second solution that is better than more innovative than what the client asked for. And now to do this, the designer must understand the business thoroughly. For instance, Cross given us an example of somebody who wanted a sewing machine redesign. What happened was the designer learned how to sew, spent about a week doing a lot of sewing projects, and then came back with a design that was very innovative and really worked with how people sew. Now, the same thing happens in data science. Data scientists, we listen to the original request and then try to do something better than what we got asked for. Now, often it can be necessary to first give the requester exactly what they asked for in order to then have the conversation of what will actually work. And to do this, we have to understand the business thoroughly and completely. Let me give an example. I was working with a bank. We wanted to increase our deposit products. That's stuff like checkings, certificates of deposits, that kind of thing. And I was come to by executives. They wanted a huge matrix of propensity models. Like, is somebody with a home loan but no credit card likely to take a checking account? Well, I thought about this a bit. I could have had work for years filling out their matrix, but I realized there's a way of doing it with just one model. Take a look at our client base. Make a expected balance based on their current stuff, a current stuff with us, and then also take a look at things like econometrics of their area. For instance, in the zip code, we could get IRS data on net income in that zip code. From there, build an expected deposit balance. Then look for customers that had a big difference between what their actual balance, their expected balance. Go after that gap. The company was doing a whole bunch of things to try to improve deposits. My model worked. It worked. It was simple. It was universal. Now, context is everything. If I'm going to make these solutions, I have to understand the context. And Cross interviews a Formula One designer. This is for racing cars. And if I'm going to have a widget, the widget has to work in terms of making the car, in the context of the car, go faster and win races. So I've got the widget in the context of the car, in the context of races. Now, in data science, we've got the same kind of context onion that if I'm going to build a model, it's not just enough for the model to have good model metrics. The model has to work in an application. That application has to work in the context of the business. Understand the whole onion to build the center of the onion, the model. Fourth principle, play is good. Designers, they'll do a lot of sketches, a lot of ideation, a lot of messing around with ideas, sometimes making physical mock-ups. For instance, the person who designed the Palm Pilot, the guy made an actual wooden mock-up of a Palm Pilot and asked himself how he would want to use this thing. And in data science, we also want to do a lot of data exploration just for its own reward, just to be curious. Not not just we have to do it to build models, but just not just this narrow model track. For instance, I was working with a wireless communication company. They had split churn, that's attrition, into voluntary, people calling us up to end their service, and involuntary, people stopping paying the bills, and then we canceled their account. People studied voluntary churn, they ignored involuntary churn. And I realized there was a chance to ask questions nobody else was. And I was able to generate a whole lot of business value from understanding involuntary churn. The fourth principle, external testing. Ideas, if I've got a design solution, I'll present that to stakeholders. Once stakeholders agree on the thing that it's going to work, we'll do sample launches, focus groups, all that stuff before the full commitment to launch. Likewise, models. Our work will be presented to stakeholders, and once we get stakeholder approval, we'll then be A/B tested very carefully to make sure our stuff actually works. Now, there's something interesting about all these 4 points that I want to hit on, that all of them, they're all necessary, and they're all anti-patterns. So let me back up a bit. Um, it is a software anti-pattern, or a software developer to critique and work with and change a spec. Don't do that. Stick to your silo. Assume the spec is given to you, solve the spec. Second off, if you're solving the spec, don't worry about context. Even in software, don't worry about the code in somebody else's work. If it works, if they do their job, you don't care. You don't care about the context. That's necessary to write code. Anti-pattern. Don't write code for the sake of writing code. That's great on your day off, but in your job, don't do a lot of work just to work, just to muck around. And lastly, in terms of external testing, I mean, software development has a whole lot of testing, but there are things like very well-defined unit tests, integration tests, clear tests with clear success failure. A software developer would never say, show his functional code to an executive to get approval. So we've got a whole bunch of situations of data science patterns being software development anti-patterns. And I want to conclude with an extended comparison with website design. Both websites and data science have their foundations in code. Now, about websites, why don't we just have the software developers do the website design? Well, the sites run really nice and look really, really bad. Now, if website designers are so good, why don't we have them to do the back end work as well? Wouldn't it make sense for one team to handle everything? Nah, that doesn't work either. Real good back end work is its own skill set and its own mindset. Now, this is all true in data science, that it doesn't work out very well to have software developers build models. And it doesn't work very well to have data scientists, data science researchers handle all the implementation. This is a known anti-pattern. Design and data science are team sports. And one last thing here. If I want to think purely in terms of the software development programming silo, how can I explain this stuff in terms of software development terms? And the answer is I can't. This is all orthogonal to the development silo mindset. So that's where I'm at. I think the next thing I want to do is project management design lessons for data science to extend this. And until that video is up, I'll see you later. Bye.